Dear friends, environmental problems are serious and we have seen that there are different types of policy instruments that government operates and implements, ranging from command and control to uniform standards to tradable pollution permits. Now we are interested in investigation that how such policies are designed and implemented in practice. It is a complex process that how government involves in controlling environmental degradation and what response it gets. The plea is that government must use scientist evaluation of an environmental hazards to formally assess the environmental problem and the risk it poses to society, a procedure referred to as risk assessment. On the other hand, the public officials must decide an appropriate course of action or policy response to reduce the risk part of the process known as risk management. Hence, in this module, we shall try to understand and analyze three important things. Number 1, the concept of risk. Number 2, the assessment of risk. And number 3, the management of risk that we encounter while designing and implementing the policy to controlling the environmental damages and hazards. In matters of risk assessment and risk management, we have to take decision and decision making is difficult since there involves uncertainty about environmental hazards and the implications for human health and the ecology, particularly in the long run. Moreover, there is no clear consensus about the government's response to given hazard. In reality, all environmental risk cannot be eliminated, hence policymakers have to determine how much risk society can tolerate and what policy to use to achieve whatever risk level is deemed acceptable. If we take an economic approach, then the management of environmental risk must be guided by the cost and benefits associated with abatement. However, sufficient data to assess the cost and benefits are not available, hence the policy makers have to rely on the best available estimates or to use an alternative risk management strategy. A. Concept of risk. We know that risk is very important concept in economics, especially in the study of entrepreneurship, but it is an obscure concept and in real world we take some intuitive sense of what it is. It can be reckoned as the chance of something bad happening when we say that things are risky. We mean that some positive or favorable outcome is not always possible. The negative event phenomenon and action wherein loss is incurred is a situation of risk. We know that risk is a pervasive phenomenon and also know that some risk can be minimized or avoided provided they have been recognized. This suggests that dealing with risk involves two tasks. Number 1, identifying the degree of risk, and number 2, responding to it. These two tasks are evolved in individual activities. Individuals make perceptive of risk in unscientific way and guided by instinct or subjective element. A person might choose to accept risk as is but also find ways to reduce it and avoid it tactfully. This shows that dealing with risk is strictly private exercise, but the risk analysis is also an important part of public policy development. The government devises it by taking into consideration of society and the social interest. The policymaker must use a systematic assessment of risk before devising a policy response. Classifying risk, voluntary and involuntary risk. One of the more common approaches is to consider two broad risk categories, voluntary risk and involuntary risk. Voluntary risk. These risks are those that are deliberately assumed at an individual level and it is a result of a conscious decision. Most voluntary risks are from personal activities such as driving a car, flying an airplane or taking drug. These risks are self-imposed and individual can make decision to respond to them. Then they adjust their exposure level to underlying hazards. Involuntary risk. When people are exposed to hazards that are beyond their control, then such risk is involuntary. These risks do not arise from a willful decision. For example, likelihood of property damage and personal injury caused by a natural disaster. The risk of being harmed by natural calamity is not self-imposed environmental hazards, such as air pollution on toxic waste sites, are another source of involuntary risk. All these risks and hazards are causing problems of human health and ecology, and they cannot be reduced to zero. Such risks are beyond the control of private individuals. They are the threats and a public problem, and government intervenes to remove such risk. Distinguishing between voluntary and involuntary risk. The distinction between the voluntary and involuntary risk is that the voluntary risk turn into involuntary. For example, smoking is a voluntary risk, but the bystander or the companion is adversely affected by it, which he cannot control it. In this regard, government has to take some measures to avoid such risk by advertisement and by caution or by anti-smoking posters, etc. Defining environmental risk. Environmental risk is an involuntary risk of exposure to an environmental hazard, which is an important concern of environmental decision makers. This risk is involuntary and it appears in the form of pollutant emissions and toxic substances. The two elements, the hazard itself and the exposure to hazard, determine the extent of environmental risk. Hazard means a source of the environmental damage. It is a form of negative externality such as poisonous factory emissions or toxic chemicals dumped into a river. Exposure refers to the pathway between the source of the damage and the affected population or resource. Both hazard and exposure define environmental risk, and each can independently affect the outcome. Since risk analysis is central to environmental decision making, the policy makers have devised methods to assess, characterize, and respond to environmental risk. These interdependent methods are referred to as risk assessment and risk management. We can discuss them separately in detail. B. Risk assessment. Risk assessment refers to the qualitative and quantitative evaluation of the risk posed to health or the ecology by an environmental hazard. In practice, environmental risk assessment is conducted by scientists who gather, analyze, and interpret data about a given contaminant. We can briefly examine each of these assessment processes in turn. Number 1. Human health risk assessment. The risk assessment model usually takes into account evaluations of human health risk. It helps to know that this risk assessment model is a part of a three-phase framework of risk-based decision making. Phase 1, problem formulation and scoping. Phase 2, risk assessment. Phase 3, risk management. The risk assessment phase is comprised of 4 steps: hazard identification, dose response assessment, exposure assessment, and risk characterization. We shall discuss these steps one by one and represent them in figure. A. Hazard identification. In this step, we determine whether a causal relationship exists between a pollutant and an increased incidence of adverse effects on human health and whether their effects are likely to arise. This determination is based on available data using several scientific methods to gather evidence about any association between human health and exposure to a pollutant. 3 common methods are case clusters, animal bioassay, and epidemiology, which we will show in a tabular form. B. Dose response assessment. This technique is a quantitative relationship between dose of contaminant and corresponding reaction. Once a substance has been identified as a hazard, scientists must investigate its potency by quantifying the human response to various doses. This element of risk assessment determines the dose-response relationship. At the hazard identification stage, dose-response assessment attempts to develop a complete profile of the effects on an environmental pollutant. An important aspect of this assessment is determining whether some range of exposures to the hazards from 0 to some specific level to tolerated. Scientists call this a threshold level of exposure, which is the point up to which no response exists based on scientific evidence. Estimating a dose-response relationship requires to make initial assumptions. These include which factors are being controlled when defining the relationship and what the underlying relationship looks like. Figure 2a, b and c illustrate three hypothetical dose-response functional forms. Phase 1, Phase 2, problem formulation and scoping, risk assessment, qualitative and quantitative evaluation of risk, hazard identification, dose response assessment, exposure assessment, risk characterization. Phase 3, risk management, formulating policy responses. Risk. Table 1, scientific methods to identify an environmental health hazard. Scientific method and its definition. Case cluster, a study based on the observation of an abnormal pattern of health effects within some population group. Animal bioassay, a study based on the comparative results of laboratory experiments on living programs both before and after exposure to a given hazard. Epidemiology, the study of the causes and distribution of disease in human populations based on characteristics such as age, gender, occupation and economic status. To each graph is positive relationship between dose level and response. What differs among them is the rate at which the response increases with the dosage. Panel A shows a linear dose response function, meaning that the rate of increase between dose and response is constant. Because the function starts at the origin, no threshold level is co-observed. The function in panel shows a constant rate of change between dose levels and response beyond dose level up to and including that point there is no response, meaning that there is a threshold panel. C depicts a cubic relationship increasing at increasing rate and then increasing at diminishing rate, drawn from the origin, showing that the response level increases at an increasing rate up and then increasing at a decreasing rate thereafter. The scientific results derived from hazard identification and dose response assessment provide general information about an environmental risk based on some known population defined by the laboratory or test conditions. This information can then be used as a basis for assessing the risk to a potentially exposed population on a specific context. The EPA Environmental Protection Act has established a database of identified environmental hazards and their relationship estimated dose response relationships for use by both researchers and the general public, referred to as the Integrated Risk Information System IRIS. This database is designed to improve risk assessment by lending consistency to what is a difficult and time-intensive process. C. Exposure assessment. The process through which a generalized dose-response relationship is applied to specific conditions for an affected population is called exposure assessment. This evaluation measures or estimates the following. Number 1, the magnitude, frequency and duration of exposure. Number 2, the pathways from the source to the affected population and the routes into the body. Number 3, any sensitivities within the population group. The sources of leads are factory emissions, lead acid batteries and lead water pipes. D. Risk characterization. Risk characterization communicates the nature of the expected risk, information on how risk was assessed along with underlying assumptions and uncertainties, and areas where policy decisions are needed. It includes the individual characterization of the 3 prior steps as well as an integrated analysis of the overall process. The description includes both a quantitative and a qualitative risk evaluation. The quantitative component identifies the magnitude of the risk and provides a way to compare one risk with another. Drawn from the dose response assessment, risk can be measured as a probability that an event will occur or as a reference dose. Environmental risks such as no carcinogenic health risks are quantified as the exposure level to a hazard that can tolerate a lifetime with harm. This is communicated as a reference dose RFD, expressed as RFD is equal to milligram of a pollutant per body weight per day. The qualitative component of risk characterization gives content to the numerical risk value. It gives a description of the hazard, an assessment of exposure that notice any susceptible population groups, and identification of the data used, the scientific uncertainties, data gaps or measurement error that distinguish the findings are pointed out as well. All this information characterizes the reliability of the results and facilitates further research. Number 2, ecological risk assessment. An ecological risk assessment evaluates the probability of changes to the natural environment that are linked to such stressors as pollution exposure or climate change, for example, crop damage and soil contamination. The present figure can give some insight into the ecological risk of climate changes under most public policies, that economical changes are viewed as secondary to human health effect. However, ecological effects and human health effects are not independent. Over time, human health is adversely affected if ecological health deteriorates. For example, damage to soil and crops may negatively affect economic productivity, human fitness, and the quality of life. A report on environmental risk by EPA devotes more attention to reducing ecological risk and to recognizing the link between ecological health and human health. The EPA has developed guidelines aimed specifically at ecological risk assessment. These guidelines help with the implementation of 3 phases comprising ecological risk assessment. These phases are identified as problem formulation, analysis, and characterization, which can be represented by this figure. Phase 1, problem formulation, information gathering about what is at risk. Phase 2, analysis, determination of what is exposed, degree of exposure, and likelihood of harmful ecological effects. Phase 3, risk characterization, description and estimate of risk based on information collected in phase 1 and 2. A. Problem formulation. In problem formulation, The ecological entity or assessment endpoint identifies the potential risk. This entity could be either individual plant or annual species, an ecological community, an entire ecosystem, or a habitat. The assessment determines that which characteristic of the entity may be at risk and what is its importance, such as its role in ecosystem. Such model shows the possible links between the ecological entity and the environment stressor with an accompanying description that include the assessment endpoint, that is, the predicted effects on the ecological entity. B. Analysis. The analysis phase identifies all the information necessary to predict ecological responses to environmental hazard under various exposure conditions. It includes that a determination of which ecological entities are exposed, the degree of the exposure, and the likelihood that harmful effects will arise because of that exposure. To support the analysis, calculations are made to quantify the risk, such as a hazard quotient, which forms the ratio of a contaminant concentration to some screening benchmark, and a bioaccumulation rate, which measures how pollutants are taken up by an ecological species. C. Risk characterization. This final phase of ecological risk assessments is a description of risk based on the information gathered in the previous phases. This description provides the degree of confidence in the risk estimate, any evidence that supports the findings, and an interpretation of the predicted ecological effects. It includes the risk descriptions as the severity of the damage, the time over which the damage occurs, and the extent of damage in terms of numbers and types of species. C. Risk management. Risk management is the decision-making process of evaluating and choosing from alternative responses to environmental risk. The objective of risk assessment is to identify risk and the goal of risk management to respond to it. The risk management is concerned with evaluating and selecting from alternative policy instrument to reduce society's risk of a given hazard. To evaluate various policy options, the decision maker must consider not only the information given by the risk characterization, but also such factors as technological feasibility, implementation cost, and other economical implications. Implementation of the risk management process involves a series of decisions aimed at two major tasks. Number 1, to determine what level of risk is acceptable to society. Number 2, to evaluate and select the best policy instrument to achieve that risk level. Since the decisions are not one-dimensional and cannot be made with complete objectivity, we use strategic approaches to guide the decision making, and some of them are mandated by law. A brief discussion of these two tasks of risk management gives us the groundwork for an analysis of risk management strategies. Number 1. Task of risk management. A. Determining acceptable risk. The general objective of all risk management strategies is to reduce risk. The policymaker has to decide as to how much risk reduction is appropriate. Since risk is a function of both hazard and exposure, we need to select any one, say exposure, and then control it. So when the risk manager decides on the risk reduction to be achieved, the exposure level is implicitly determined. In setting the level of acceptable risk, the policymaker confronts a difficult but necessary question: should the policy eliminate the risk by reducing exposure to zero, or should some compromise be struck at some positive risk level, and if so, where? Acceptable risk is the amount risk determined to be tolerable for society. If the acceptable risk level is set at 0, the policy must reduce society's exposure to 0, although this action eliminates the associated health and ecological damages, but the factory or plant would be closed and lead to unemployment. If some positive level of risk of deemed acceptable, then the decision maker is setting policy that allows exposure and therefore some amount of damage. To help guide this difficult decision, policymakers sometimes use the concept of de minimis risk. De minimis risk refer to a negligible level of risk such that reducing it further would not justify the cost of doing so. This concept is sometimes equated to the risk of a natural hazard. For example, earthquake. Once the baseline is established, the decision maker might use comparative risk analysis to evaluate how the positive risk level compares to other currently faced and accepted by society. This type of analysis can be useful to communicate the relatively unfamiliar risk associated with exposure of naturally occurring gas that can be harmful. B. Evaluating and selecting a policy instrument. After ascertaining the degree of risk and the need of a required policy is determined, the next task of risk management is to decide the type of policy useful for that. Here the question of evaluation of alternative policies arises. The policy that gives the acceptable risk level and can serve the purpose is selected. We know that there are two policy options, either to go for command and control or to go for market based policy. Here the risk manager takes into consideration the magnitude of risk and the cost benefits related to each available control instrument, and hence in this situation the risk management strategies enable us to evaluate a policy instrument. Number 2. Risk management strategies. Executing the two tasks, namely determining the acceptable risk level and choosing the appropriate. Policy instrument requires a systematic evaluation of available options. From an economic perspective, the most important considerations are: number 1, the level of risk established; number 2, the benefits that accrue to society from adopting the policy; number 3, the associated cost of implementing the policy. Many risk management strategies have been developed over time, each of which outline how these factors are to be evaluated. The most prevalent of these are comparative risk analysis, risk benefit analysis, and benefit cost analysis. A. Comparative risk analysis. This analysis helps the risk manager to select an acceptable risk level as well as to officials to identify which risks are most in need of an official response. The EPA's Science Advisory Board (SAB) has prepared a ranking of environmental problems by degree of risk shown in the table. Relative risk ranking and associated environmental problem. High risk to human health, ambient air pollution, worker exposure to chemicals in industry and agriculture, indoor pollution, contamination of drinking water, high risk to natural ecology and human welfare, habitat alteration and destruction, species extinction and loss of biodiversity, stratospheric ozone depletion, global climate change, medium risk to natural, ecology and human welfare, herbicides or pesticides, contamination of surface water, acid deposition, airborne toxics, low risk to natural ecology and human welfare, oil spills, groundwater contamination, radionuclides, thermal pollution, acid run off to surface waters. The SAB specifically advises that EPA programs should be guided by the principle of relative risk reduction, meaning the agency should order its policy decision to reduce the most severe environmental risk first. The difficulty with setting risk-based priorities is the difference between the government's risk setting and the risk perceived by the society, which is depicted in Table 2. To see a ranking of environmental problems based on general public perception in US. Environmental problems and the percentage responding that problem is very or extremely serious. Hazardous waste 89, oil spills 84, air pollution 80, solid waste disposal 79, atmospheric damage 79, nuclear waste 78, contaminated water 77, forest destruction 76, ocean pollution 75, endangered species 67, threat to wildlife 65, pesticide use 60, world population 57, poor energy use 56, global warming 56, reliance on coal or oil 53, wetland development 50, radon gas 35, indoor air pollution 27, electromagnetic fields 19. Notice that public perception of environmental risk is generally not aligned with the SAB's ranking given in this table. Such dichotomy of views between public perception and scientific evidence presents a dilemma to officials attempting to gain support for policy proposal. In this condition, government should communicate scientific findings to the public to improve its understanding of environmental risk. Comparative risk analysis enables us to select appropriate control instrument from given alternatives. This approach is often called risk analysis. This strategy involves a comparison of the estimated risk probabilities or risk ranking scores from two or more policy options. This also gives access to the decision maker to compare the relative risk involved in given hazards and choose the instrument which is more effective in reducing risk. It implies that the objective of a risk strategy is risk minimization with no explicit consideration allowed for associated cost. B. Risk benefit analysis. Risk benefit analysis deals with an assessment of risk of hazards along with the benefits to society if not regulating the hazards. In this approach, risk is taken as a cost and is compared with the benefits of the usage of risk hazardous resource. For example, the use of gasoline, creating gas is health-wise a risky hazard for the society, but at the same time, the usage of gasoline provides a source of fuel to society. In this situation, the risk manager compares the risk reduction strategy with the benefits. He would maintain the balance between the two. He would consider that how a reduction in gasoline usage would diminish society's well-being. In this analysis, in short, the risk manager has to keep in mind while selecting the instrument the degree of exposure to the substance and the benefits the substance provides to society in use. C. Benefit cost analysis. This analysis can identify an acceptable risk level based on the criterion of allocative efficiency. For incremental risk reductions, the decision maker would compare the monetized value of social benefits with the associated cost to find the efficient risk level, where the marginal social benefit MSB and the marginal social cost MSC of risk reduction are equal. This corresponds to the risk level that maximizes the difference between total social benefits TSB and the total social cost TSC. Environmental law is meant to achieve risk reduction to the associated benefits which are predetermined. In such cases, the risk manager still can use benefit cost analysis, but with different objectives in mind. Here the goal would be to select a policy instrument that meets the legislated risk objective at least cost. If the selection is made properly, initiative will achieve the economic goal of cost effectiveness rather than allocative efficiency. If the risk manager finds that at risk level the MSB and MSC are not equal, then he would think to amend to correct the resource misallocation. Conclusion: we have seen in this module the concept of risk, risk assessment and risk management in the context of environmental policy to overcome risk hazards. In fact, the environmental decisions are difficult and controversial. However, the environmental policy makers struggle as to how to bring objectivity and fairness with the risk posed by environmental hazards. It is a point effect of scientists, researchers and officials to get information about the nature of environmental hazards and the risk exposure. Risk management strategies enable to determine the acceptable level of risk and appropriate policy instrument to equate MSB and MSC. The use of benefit cost analysis as a decision rule is becoming more prevalent in public policy decision making. Monetizing environmental cost and benefits is an attempt to provide an impartial guideline to the risk manager. Thank you.